Hi everyone, welcome back to Chapter 3. Just a quick recap here. Chapter 3, we started to talk about averages, and we gave examples of 3 different kinds of averages that are often used in behavioral sciences, and they are the mean, the median, and the mode. And let's see, we defined what an average is. We talked about it being a typical or representative score that stands in for a larger data set. So just give me one number to give me an idea of what those numbers look like. We also talked a little bit about the mean and how you can calculate the mean of a sample, in which case it would be this green box here. And we talked about the mean of the population. So if you calculate the mean of a sample, what you're doing is you're calculating an estimate. And if you calculate the mean of the population, well, that's a parameter. Okay. We also talked about how you can't really figure out whether or not somebody calculated an estimate or a parameter based on the size of the sample, because estimates can be very, very large. And they can be very small. And the same thing with parameters, right? The population can be very large or very small. And that's kind of where we left off. And so today what I want to do is finish talking about the mean. We're going to cover some properties of the mean that I'm betting a lot of you don't know anything about. We're going to then shift our attention to the median. And again, we're going to look at some properties that I'm pretty sure that most of you are unaware of. I don't know that we're going to get as far as talking about the mode today, so that's going to have to be a wait and see. All right? Okay, so moving on then. Properties of the mean. First one, X bar is a consistent estimate. Now, I bet that if you went, somewhere in Cedar City, you're walking down Main Street, for example, and if you were to stop the first person you encounter and you ask them, what do you think this means, to say that the mean is a consistent estimate? Well, you might hear somebody say that it probably means that whatever you calculate as a mean, you're going to get the same response over and over and over again. So calculate it the first time and you get, let's say, a 12. Well, if it's consistent, that means if you calculate it a second time, a third time, a fourth time, you're going to keep getting 12 or somewhere around 12. Now, normally your intuition, I think, would serve you well, but this is not a case where your intuition does just that. It actually fails you, because a consistent estimate means something very, very specific in statistics. So a consistent estimate means, in this case, we're going to use the X bar as an example. So as the sample size increases, the mean, so that's of the estimate, gets closer to the mean of the population, mu. Now, this is a very specific definition as it relates to X bar or M and mu. All right, so as you take larger and larger samples, your estimate, X bar, the mean of the sample, gets closer to the mean in the population, at least in theory. All right, if you actually tried to do this, you could get some estimates that come from very large samples, and they're not at all close to the mean of the population. But in general, we do expect that the larger our sample size, the better our estimates will be. I mean, that just, I guess, makes good sense, right? So let's run through an example so that you have a better understanding of what this means. Now, everybody wants to know where I'm pulling these numbers from. That's a common question I get. I pulled them out of my head, from the dark recesses of my brain. I just said, I need a number from you. What should it be? And 50 popped up. And then I said, what do I need or what do I want for a sample size? Oops, I'm sorry, a population size. And this time, 100 popped into my head. The numbers that pop into my head are almost always really, really simple numbers. All right, so just an FYI. There's nothing special about them. I just invented them. came up with them randomly. Okay, so let's start with a very, very small sample from this population. So let's pretend we reach in, and for sample 1, we have 10 scores from the 100. And let's just say we calculated X bar and it equals 32. So the mean of the sample equals 32. Remember that M, this M here that's capitalized and italicized, that is the same thing as X bar, okay? All right, so with a very small sample size, we end up with an X bar, and you can expect that that X bar is probably going to be pretty different from the actual mean in the population. In this case, it's 18 points off, okay? And we kind of expect that with a very small sample size. We don't expect our estimates to be very good estimates. They're going to be off by quite a bit. Now let's say we reach in, so here's sample 2. This time when we reach in, we grab 30 scores out of the 100. I'm sorry if I said 50 before. I'm not sure that I did or didn't now, but if for this one, if I said we reach in and we get 10 of the 50, that would have been a mistake, right? We reach in, we get 10 out of the 100 possible, just to clarify. Okay, so for sample 2, then we reach in, and this time we get 30 scores out of the 100. And we calculate X bar for this sample size, and it's 38. Now, in theory, when we take a larger sample size, we should get a mean that is closer to the mean of the population. And in fact, this time, instead of being 18 points off, this time we're only 12 points off. Now, I am coming up with numbers here to reflect what we should see as a trend in theory. I don't know that we're going to get 32. I don't know that we're going to get 38, but in theory, with a larger sample size, we should get an estimate that is closer to the actual population mean. Okay? So now let's reach in, and this time we include 60 of the 100 possible scores. And according to the theory, X bar should now be even closer to the population mean. Now, this time it's only 5 points off, right? Notice sometimes when we calculate an estimate, like these two here, they were underestimates. They came out lower than the actual mean. But for sample 3, we were 5 points away, and this time it was a bit of an overestimate. But we were closer, right? We were only 5 points away. So sometimes when we take an estimate, we're going to get underestimates, and sometimes we're going to get overestimates. All right? But again, the point with saying that X bar is a consistent estimate, what that means is as we increase our sample size, X bar does in fact get closer to mu, at least in theory. Okay, now let's get ridiculous. So sample number 4, you have 99 of 100 possible scores. If that ever happened, I would kick your butt back out there and say, get that last person, get that last score. But let's say, because this is only a hypothetical situation, hypothetically, you got 99 and you just couldn't reach that 100th person. Now, with all but one score in your sample, you would expect X bar to be really, really, really close to the 50, right? Because you're only missing one person's score. So in theory, you should be very, very close. All right. Now, I have some thinking cap questions for you, and this will, I guess, test your understanding of the concept. And so let's look at the first thinking cap question. Even if we were missing just one number, so here we said this last example, we said we're missing just one number. It is still possible that the mean of the sample might not be as close to the mean of the population as we would expect. Because again, in theory, we would expect it to be very, very close. But there is a specific situation when even missing one number we could still get an X bar here that is far off. Can you think of when that would happen? So what number might you miss that could still give you an X bar that is really, really different from the population mean? Well, think about this. What if the one number that you're missing happens to be an outlier? We're going to talk more about outliers in this chapter, but just really quickly, an outlier would be an extreme score that is unlike any of the others. So let's say all the scores in our sample were, let's say all the scores in our population, let's say all the scores in the population are between, 1 and 10, okay? Except for one person's score, which happens to be 1,000,000. Okay, so paint that picture in your head. So in the population, all the scores are between 1 and 10, except for one specific person who has a score of 1,000,000. What if that person that has a score of 1,000,000 was the one person that you didn't get in your sample? Then you would have an X bar that was very different from the population mean. And it's all because the one score you happen to miss was the one outlier. Okay? So it's, a lot of things that we talk about in statistics is based on hypotheticals. And so we have to plan for these hypotheticals. And so if somebody says or asks you, how accurate do you think your estimate is? Well, you can say it's probably good or probably bad, and you're going to use sample size to help you answer the question, right? If you had a really, really good sample size, then you can say my estimate is probably pretty good because look at my huge sample size. But again, what if you were missing the outliers from your sample? Then maybe your estimates aren't very good. And that's why in statistics, we always tell people, well, it's probably good or probably bad or probably true or probably false. We always put that word probably because unless we test the entire population, we really don't know. What if our sample is missing the outliers, right? Again, we just don't know. All right, let's try the next question. How about this? Complete the sentence. As n increases, now remember n is sample size, as n increases, the value of the estimate gets closer to the value of the parameter. Remember that estimates are estimating parameters. Up here, we gave a very, very specific definition of X bar as a consistent estimate. So if I'm asking what does this mean, then we say, well, as sample size increases, X bar or M, X bar gets closer to mu. Now that's with X bar, but you might have another statistic, not the mean. All right, let's say your statistic is S squared, just by example. Okay, so if it's S squared and we say S squared is a consistent estimate, then what do we need to change? Well, we need to change this and this. So we would say as S squared, as sample size increases, S squared gets closer and closer to, well, what is S squared estimating? Sigma squared. So we would plop in sigma squared here. Okay, so just generically, if we say what is a consistent estimate, we would say that a consistent estimate is one where as sample size increases, the value of the estimate, whatever that is, gets closer to whatever it's trying to estimate. So in other words, it gets closer to the value of the parameter. Okay? So sometimes you'll be asked to give these generic definitions and sometimes more specific definitions. And you have to read the question very, very carefully. All right, so if it's phrased like this, I'm not asking about any specific estimate. So that means here you have to put parameter. You can't say a specific parameter because you don't know what the estimate is. If you struggle with this, let me know. I'm here to help. All right,